We all love our Arduinos and ESPs, but do we know or remember where they came from? Today we start a journey back to the late 1970s and early 1980s, where the personal computer journey began. The chips used then were simple and gave honest feedback. That is why we can learn a lot about today's chip. Do you want to accompany me on this journey? Grüezi YouTubers, here is the guy with a Swiss accent, with a new episode and fresh ideas around sensors and microcontrollers. Remember, if you subscribe, you will always sit in the first row. Today we will start by looking at the different parts and tools used back then. We will try to find the roots of our microcontrollers used in the Arduinos. We will use Intel's 8085 family of chips. We will look at the different parts like CPU, different types of memory and peripherals. We will work with EPROMs, which is very old-fashioned. We will have to understand address and data buses. We will deal with addressing different chips and so design a memory map. We will learn how to demultiplex addresses from data. During this work, we will learn a little about the famous 74XX chip series. In the end, we have a schematic for a simple single-board computer with 8 KB of EPROM, 2 KB of RAM, a timer, and 24 I/O pins. Not bad for the 1980s. Based on this schematic, in a future video we will create our own small computer and write some code for it. But let's start with today and with the MCU used in the Arduino Uno, the Atmega 328P. If we look into the datasheet, we see that the chip has 24 pins. Apart from VCC and ground, we also see a pin for reset and 2 pins especially for the analog to digital converter. All other pins are multipurpose I/O pins. If we look inside the chip, we see a CPU, different memories called flash, EEPROM and SRAM, and some logic to run the CPU like an oscillator and a reset logic. Then come various subsystems like timers, counters and so-called ports that can be configured to read external data or output data to the environment. And to read analog signals, we have also a built-in ADC. We do not have a DAC, a digital to analog converter, to create analog signals. We still have to use tricks for that. One important thing not shown on this chart is the matrix to connect these subsystems to pins. This is the secret behind the flexibility of these chips. They make it possible to connect one physical pin to different subsystems inside the chip. As an example, we can connect pin 10 of the chip to a quartz resonator, a timer, and to the interrupt system. Without this matrix, such a chip would have 60 or more pins. When we step back in time, you will see that we find most of these functions already in the 1980s. But of course, like haircuts or clothing, they were a little different back then. When we start our journey, the first question is, where do we get the parts from? And are they still manufactured? First, you still can buy most of the essential components to create your own retro computer. I think most of them are no more manufactured, but still available in so-called old stocks. I also bought some EPROMs from AliExpress. These parts definitely have a different history. They are recycled parts that came in this exciting packaging. They survived 30 years in other devices, so they will also withstand the transport in this plastic packaging. At least all were without content, so I was not able to find out in which manufacturer's device they had their first life. Now we already arrived in the middle of the story, which started around 1978 when I got my first personal computer, a TRS-80 with a C80 processor, running BASIC. After learning BASIC, I started using assembler on the TRS-80 and later built my own hardware. The C80 was a fine CPU, but too complicated for single-board computers. The 8085, on the other hand, was able to run most of the C80 commands. and he was part of a system of peripheral chips, which reduced the complexity of boards considerably. Precisely what I was looking for. By the way, back then these CPUs were not extremely expensive. Below 10 Swiss franc, if I remember right. Which is maybe $30 these days. The expensive stuff was the development system with memory, floppy disks and printers. What do we need to build such a single board computer? A CPU for sure, if we remember the block diagram of the ATmega 328. Plus memory and peripherals. Let's start with the 8085 by having a look at its datasheet. It shows registers and signals with unique names like ALE or ready. This diagram clearly is one level below the block diagram of the 328P. This is what happens with everything around us. Each generation goes up the abstraction ladder. The complexity humanity has to deal with is always about the same. It just moves up on a higher level, as we will later see. The 8085 definitely has no I/O pins and also no memory. If we compare the chip with the 328P, we see that it is much bigger and has more pins. Why that? Because in the 1980s, everything was still parallel. Serial connections were sporadic. Why? Because parallel connections are much easier to implement. They can be much slower than serial connections with the same capacity. If we want to replace an 8-bit parallel bus with a serial connection, it has to run at least 8 times faster than the parallel bus. This is why you could call the 1980s and 90s the ribbon cable age. Now we are in the serial cable age. Let's continue and look at the majority of pins. They have names like AD0 to AD7 and A8 to A15. What do these names mean? Each CPU needs 2 sorts of connections, an address bus and a data bus. The size of the data bus usually has the same width as the internal registers. The 8085 is an 8-bit computer with 8 data lines. The width of the address bus, on the other hand, decides on the maximum addressable memory. Here it is 16 bits. Let's count the pins. 8 for data plus 16 for addresses are already 24 pins. Plus VCC, ground and reset we are already at 27 pins. From the 40, only 13 are left for all our other desires. And even worse, we need additional pins to communicate with the external memory. We have to flag if we want to read from or write to the memory. 2 extra pins. The resonator needs another 2 pins. Now we are below 10 left and still want a few pins for interrupts, for example. This is why the engineers of Intel decided to share or multiplex the data lines with the lower 8 address lines. Now we have 8 pins more for other stuff, or at least 7 as we will later see. But also a little more work. These combined pins are called AD0 to AD7. With its 16-bit address bus, the 8085 can address up to 65 KB of memory. Yes, you hear right, not megabyte or gigabyte. By the way, these processors, as well as some of the RAM used back then, had Alzheimer's disease. They forget very quickly if you do not refresh the content. This is also why we cannot run the original 8085 slowly. It forgets the next step before it finished the actual one. This is why I ordered newer versions for our future experiments. Anyway, now we need memory which lasts for a long time to store the program and maybe some constants. And we need memory which can be written to by the processor. Now we come to an exciting thing for the young viewers. Back then we stored our programs in so-called EPROMs, erasable and programmable read-only memories. The interesting stuff is this quartz window, where you can see the chip and its bonding. This window is necessary because these chips are erased with UV light. But where do we get UV light from? We all had our secret sources for UV lamps back then, and we built our own eraser. Today we can buy this Chinese eraser. It is really a retro. It still has a mechanical timer. Excellent. One detail is astonishing. Exposed to UV light, the EEPROM loses its content in less than 20 minutes. And this EEPROM was programmed 35 years ago and still keeps its content. But of course, here the window is covered. Another exciting thing you will discover if you have one of those in your hands. They weigh much more than today's plastic chips. They are made of ceramic material. Back then, you got military versions of different chips that were packaged in ceramic materials. They had the same function, but were specified for wider temperature ranges, for example. And they were incredibly expensive. But if you wanted to build satellites, for example, you had to use these chips. The size of these chips varies. I will use a 2732 with 4 kilobyte of memory. You see, 2732 is the number of bits, which sounded a little bit more than only 4 kilobytes. Marketing was also active back then. Today, we easily could use a 27512 and would use the whole address range of the 8085 with only one chip. Two reasons speaks against using such a chip. The first, I would not have the time nor the desire to write such extended code in assembler, and the second, we need the address space also for other purposes, as we will later see. Next question. How do we program these chips? Let's look at how we program our MCUs today. We upload the code into the flash memory of our Arduinos. In the case of an ESP32, even over the air. EEPROMs, on the other hand, cannot be programmed inside the computer. We have to remove them and put them into a programmer. This is why these parts all had sockets. And this is the reason we can buy them used today. Back then, we also built our own programmer to save money. Today, we get this marvelous device that is capable of programming many different chips. Unfortunately, there is a problem with it. The first series of 2732 chips had to be programmed by applying 21 volts to one of the pins. Unfortunately, this TL866-2 only has a maximum voltage of 18 volts. So pay attention and go for the CMOS versions of the chips, called 27C32. They can be programmed with only 12 volts. And a tip, every chip, even if it is of the same type, may have different programming procedures and voltages. So always first search the right part in the built-in database of the programmer before you hit the program button. Otherwise you might produce some casualties. How were these programs stored and transported from the development machines to the standalone programmers? With Intel hex files. These were invented when the programmers still used punched paper tape to read the code. We always can use this format today, and I think it still has the biggest compatibility list. Now we have a CPU and memory to store the code. We even can erase and program our historic chips. Now we can start to build our computer. But first, we have to understand how memories work. Memories have address and data lines. If you apply a particular address to the address pins, the data lines are set according to the content programmed before. Here I have a 2732 chip on my breadboard. All address lines can be connected to either ground or 5 volts, and the data lines are connected to 8 LEDs. When we power the thing up, no LEDs lights up. Why? Because all address lines are connected to ground and the address is 0. Let's check what we stored at location 0. The programmer says 55, not 0, as the LEDs suggest. What's wrong here? The content of the chip is not transferred to the data pins and the LEDs. We have to take care of 2 additional pins which are essential for that purpose. The enable pin, sometimes also called chip select, and the output enable pins. Both pins have an inverse logic as we see here. They are active when we set them to low. Let's do that. Now a few LEDs are on and the chip works. Cool! Back to the future. 35 years old and still working. But what shall I say with my 63 years? These two pins become essential for the next concept we have to discuss. What happens if you connect two wires with different signals to the same data line? Yes, you do not precisely know which one will win. And more often than not, the signal stays somewhere between logical 0 and logical 1, which is forbidden in logical systems. Precisely this situation can happen here. Each memory chip, as well as the CPU, has data lines. They all have to be connected together. We call it the data bus. All chips are connected in parallel. To avoid problems, the chips have to use a so-called tri-state logic, where we have, in addition to the normal levels, high or low, also a state called high impedance or open. All chips are in this open state if they are not selected by the CPU. If you do it right, only one chip is selected at a particular time and can put its data on the data bus, without being disturbed by others. The two select pins discussed before force the chip into the open mode if set to high. What about the address bus? Do we also have to pay attention there? In typical situations, the CPU is the master and issues addresses. All others listen, so no problems here. You can connect all chips in parallel to the address bus, in theory, as we will later see. By the way, look at the power consumption of the chip. 125 mA, and in sleep mode still 35 mA. Not micro or nanoampere, as we expect from today's chips. Maybe that is why they built plenty of nuclear power plants back then. If we change the address to 1, the LEDs change, because I stored a different value to location 1. Now we are in the middle of the hardest part of retro computing, the hexadecimal numbers. You have to know them in and out if you deal with this technology. Why? Because in reality these chips work in the binary system, and the hexadecimal system is the same, just a little easier to handle. Especially it is shorter if you write it down. All these numbers in the programmer are in hexadecimal. It's easily visible if we load a freshly erased chip. All FF. The first F means the first 4 bits and the second F describes the second of the 8 bits. FF means that all bits are 1, and 55 says that every second one is a 0. I do not want to dig further into the matter. We get enough of that if we start to write programs for our computer. One thing to remember. Nothing is in decimal numbers. All are in hexadecimal, even if it's not marked. Because our ROM chip seemed to work, we can go on and connect it to the CPU. But wait! The EEPROM has separate address and data lines, and the 8085 has 8 shared lines. How can we deal with that? We have to demultiplex these lines, which means we have to separate the address lines from the data lines. How can we do that? On these multiplexed pins, the CPU always first sends the address. Then it waits a moment and sends or reads the data. If we would know when it sends the address, we could store it and send it to the memory chip. When the CPU requests data later, the chip would be ready to deliver. We can use a simple integrated circuit for that purpose, a octal flip-flop, as the 74-73 I use in my design. As this diagram shows, it transfers the input signal to the output pins if the clock signal rises. After that, the output stays stable until the next rising signal occurs. If we connect all AD lines to the input of the chip and get a synchronization signal for the clock pin, we get stable addresses at the output. Cool. Of course, the 8085 provides this signal. That is why we only gain 7 pins, not 8, if we combine data and address lines. Unfortunately, the so-called ALE signal has the wrong polarity for our 74-73. So we need an inverter to create the right signal. I use one of the 4 NANDs of a 7400 for that purpose. The first number of many 74XX chips is given to a NAND chip says everything about the massive importance of NAND gates, even on your computer you're watching this video. As an example, we easily can use such a NAND gate to create an inverter. They are the most versatile gates. If we connect the output of the demultiplexer to A0 to A8 of the EEPROM, we are ready to go. But the EEPROM has more address lines. What to do? We connect those directly to the address bus. Because our chip only can store 4 kilobytes, the chip stops at A11. What to do with the rest of the address lines? Just leave them open? If this would be the whole computer system, indeed we would leave them open, because we don't need them. But this is not the case, because we will add more chips. Now it's time to create a memory map. The memory map usually starts with the address 0000 and ends with FFFF if we use a 16-bit address bus. Where should I place our EEPROM if we connect it directly to the address and the data bus? You're right at the beginning at 000 to 0FFF. Are you sure? What happens, for example, if the CPU address is 1000? Maybe it's easier if we convert this number in binary. You're right, for the EEPROM it looks like 0000 because it does not see the higher address lines. So our EEPROM appears 16 times and the entire address space is used. Not good if we want to add another memory chip. What to do? We could, for example, use a 4-input OR chip, which has this truth table. By the way, this is an exceptional chip, and you might not find it anymore in the market as many other unusual 74XX chips. A little excursion to this famous transistor-to-transistor logic or TTL chip series, which is produced by many manufacturers. Most of today's chips are either 74LSXX or 74HCXX versions. As this list shows, you sometimes also get other versions if you need, for example, more speed. The functionality, however, is always the same. This was probably the first standardization in this industry. Very handy. If we connect the A12 to A15 to the inputs of this chip, we get a low signal only if all lines are low. If we connect this signal to the enable pin of our 2732, it only reacts if A12 to A15 is low, and we lose all mirrored versions, exactly as we wanted. Fortunately, there is a much nicer solution for that problem. We use a 74LS139 chip. It has 3 inputs and 4 outputs. If we connect A12 and A13 to the address inputs and A14 to the enable input pin, we get 4 different output signals. The truth table shows that all are low for a particular situation. Pin 00, for example, is low if all 4 address lines are low. This would be a direct replacement of our 4-input OR gate from before. If A12 is high, 01 is low, and if A13 is high, 02 is low. With such a chip, we can separate all our address space in 4 chunks of 4 kilobyte, exactly as we need for our small single-board computer. The only thing we have to do is to connect the 4 outputs to the respective chip enable pin of the other chips. If we go back to our Atmega 328P, we see that our computer still lacks I/O and RAM. Here I have a simple cure, the 8155 of the 8085 family. It offers 3 parallel ports with 24 pins, a small RAM and a timer. The RAM even is static and therefore without Alzheimer. This was a lovely chip in the 1980s. And it's fully compatible with the bus logic of the 8085. The demultiplexing is already built in. Just connect all the pins with the same names, nearly as easy as today. And of course, we connect its chip enable to O2 of the 74LS139 and adjust our memory map accordingly. Just a remark, the I/O registers are addressed differently, so they do not have to appear in our memory map. Often you see peripheral chips addressed like memories. Then, of course, they have to be part of the memory map. The rest is straightforward. We add a 2 KB RAM chip. Because we now have a proper address and data bus, we connect the new chip to those lines plus to O1 of the 74LS139. Of course, we have to connect now also the write enable, because we also want the CPU to write to this chip. Ready is our SBC. I add a 7805 and some capacitors as well as a CD4040 counter to get a clock reference for the timer inside the 8155, and also to create an interrupt. Back then, this interrupt was used to create a custom-made serial connection, because I did not want to use another big chip like the 8251. Those were the days. We had to build our own stuff because we did not have the money to buy them. Or, as one of my colleagues said, we replaced cash with time, which, without smartphones, was plenty available back then. And, as today, nerds were not particularly attractive for girls. Dancers like John Travolta were more in fashion back then. So, 16-hour days in front of my TRS-80 were not rare these days. A wonder that my sight still is okay if I remember the shitty converted TV sets we used as monitors. These times are one of the cornerstones why I was able to create this YouTube channel. A lot of know-how and stamina, if the damn thing did not work for weeks. By the way, do you remember the 8086 and the cheaper 8088 chips of the IBM PC? Both also had this multiplex bus, and the 8088 was specially made to be compatible with the 8-bit peripherals as the 8155. Because Intel was a little faster with the 8088 than Motorola with the 68008, Intel was chosen for the IBM PC. The rest is history. I tried to build this computer on my breadboard. It did not run stable, and the signals were not very good looking. This is why I decided to create a PCB. So we can continue with a PCB if we want to play with code in a later video. I know many of you have memories about these chips or similar ones. Please share them in the comments if you want. I also put a link to the drawing. Maybe you find design errors before I order it. And yes, I summarize again. We tried to find the roots of an Arduino chip, and we found many of them. We used Intel's 8085 family to step back in time to the late 1970s or early 1980s. A modern Atmel chip is a microcontroller unit or MCU, which contains a CPU, RAM and peripherals. In those days we were able to build similar things, but each function needed a distinct part, and we required some chips to glue the whole thing together. Such a system was called single board computer, or SBC, like the Raspberries of today. We learned to program and erase EPROMs, which is very nostalgic. We learned about the address and the data bus and its function. We also looked at how to address different chips and so design a memory map. We demultiplexed addresses from data and looked into the famous 74XX and CD4XXX chip series. In the end, we have a schematic for a simple SBC with 4 KB EPROM, 2 KB RAM, a timer and 24 I/O pins. Not bad for the 1980s. I hope this video was useful or at least interesting for you. If true, please consider supporting the channel to secure its future existence. You will find the links in the description. Thank you. Bye.